Hello and welcome everyone to the lesson on the shortcut rules for differentiation. So previously in lesson 1.3 we learned a long way to find the derivative of a function. And just to remind everybody, this was the definition of the derivative of a function f of x. So limit as h goes to 0, f of x plus h minus f of x over h. We talked about this at length. We did practice problems, but it's a lot of work to find the derivative of a simple function, even something like just f of x equals x squared. And we also learned the meaning of this. It gives us the slope of the tangent line to f of x at any given point x. Also, we can interpret it as the instantaneous rate of change of the function f of x at the point x. So we saw, applications and so forth, but calculating it was messy. So I have good news. In this segment, we're going to learn simpler ways to calculate derivatives. Let's begin with the basics. So for example, if we have the derivative of just a constant c, now, what is the rate of change of a constant? If you were to look at a graph, it would just be a horizontal line, right? Its rate of change is basically not existent. It's always the same. So the derivative of a constant is equal to c. And the d over dx notation is basically saying the derivative of whatever comes in front, in this case c, with respect to the bottom variable, d over d. So derivative of c with respect to x. That's how we interpret it. Okay, so derivative of a constant by itself is 0. We don't need to use a fancy formula for that. What about the second one rule? The derivative of mx plus b. If you have a straight line with a slope of m, its rate of change at any given point is going to be just that slope, right? It's always going to rise over run, rise over run. No matter where you are, that rise over run is always the same for a line. So the derivative with respect to x of a linear function in the form y equals mx plus b, you guessed it, right? It's just going to be m, the slope. So usually derivatives are not really needed for linear functions. We can easily find the derivative using slope for a linear function. It's more interesting when we don't have linear functions. That's the question, like how do you find rate of change? That's when we have to evaluate derivatives. Okay, so if you have something like x to a power, we call this a simple power function. How do you take the derivative? Now let's remember from our past experience, we had seen the derivative of x squared was 2x. And I'll also give you one more example. If you did a long formula applied to the function f of x equals x to the third, you may find the answer is 3x to the second. This would have been very long with the formula, x plus h to the third power minus x to the third over 8 simplified. But the final answer would have been 3x squared. I'm giving you a few examples for the reason of having you try to guess what the general rule will be. So I'll give you one more and I'll ask you to guess the general rule. So if you had x to the 4, it turns out that it is going to be 4x to the third. Now look at all those examples. I want to know what is the derivative of x to the n. So look, x to the third became 3x squared. So this n became the number in front, right? So n times x to a power, and the power became 1 lower than what we started with, so it's going to be n minus 1. So that turns out to be the shortcut rule for finding the derivative of a power function. And one more simple rule, we're going to go to examples. Rule number 4, if you have a constant times a function, you can pull the constant outside. So you keep the constant as it is times the derivative of the function. Notice how this rule is different than rule number 1. If it's a constant all by itself, the derivative is 0. But if it's a constant times a function of x, you can pull the constant outside and just simply take the derivative of the function. So let's take a look at a few examples to practice these rules. So for example, the derivative of x to the 7. So with the shortcut rule, it's going to be 7 times x to the power of 1 lowered, right? So it'll be 6. So basically, it's as if you're bringing the power down and you're subtracting 1 from the power. And this is doing that tedious work of applying the definition, the limit as h goes to 0, f of x plus h minus f of x over h. Everything is done. It's simplified. This is the final answer. Now, if they give you a point, like what is the derivative at the point x equals to 1, you would plug it into this and you would obtain the derivative or the slope of the tangent line at that given point. But right now we're finding derivatives in general at any point x. Okay, let's take another practice. The derivative with respect to x of x to the 10. So that'll be, again, bring the power down, subtract 1 from the power, 10 times x to the 9. Another way to ask the same question would have been, I'm giving you f of x equals x to the 10. What is f prime of x? Same thing, right? It's just a different notation. We can use d over dx notation, or we can use the f prime notation. Okay, what happens over here? We have a constant up front. Remember, constant times a function. You can pull the constant outside. This will be 3 times the derivative of x squared, which is 2 times x to the first power. And I want to put the 1. So this is the same as 6x. So if there's a constant up front, just keep that in your mind, the 3, and then take derivative of x squared and multiply the 2. You don't even have to show me this step. It's okay to go directly to that. Like, for example, derivative of 5x to the 4th. So 4 will come down. I'll have 20x to the 3rd. What happens with things like fractional situations, like 1 over x to a power, or radicals? We need to remember a few rules there. First of all, you should always try to rewrite the given function as x to a power if you're going to apply the power rule of differentiation. So I need to remember, okay, 1 over x is the same as x to the power of -1, right? When you bring it up, whatever the power was here, it becomes a negative power, right? Now I'm taking the derivative then of x to the -1. What's the derivative of x to the -1? And we can apply the same rule. So you bring the power down and subtract 1 from the power. So -1 minus 1 is -2. And usually we like to rewrite everything without any negative exponents. The negative up front stays, divided by x to the positive second power in the denominator. So x to the -2, it can be written as 1 over x squared, and there was a negative up front. What about something like, let's do this one, another one with a fraction, 6 over x squared. What is the derivative? First, let's write 6 over x squared as 6 times x to the -2nd power. Notice I'm still keeping the d over dx notation here because I have not taken the derivative yet. All I have done is rewrite this expression like this, okay? Now I'm going to take the derivative. That's when the d over dx notation will disappear. So the derivative of this will be, so bring the -2 down, be -12, subtract 1 from the power, x to the -3, and let's rewrite everything. -12 divided by x to the +3. Again, good common practice to leave the answer in terms of a positive exponent. Now let's do a few involving radicals. So for example, the square root of x. Okay, we did this one in the last section. It was long. Remember, we had to multiply top and bottom by the conjugate because we're applying the basic definition of the derivative. Here it's going to be a lot easier. And just it's important to note on the test, some questions will say, do it using the definition. So that's when you use the long method. Some will say, if it didn't mention anything, it's okay to go with the shortcut rules. And notice now that you know the shortcut rules, you can always check your answers even for the longer problems. So that's a huge advantage you will have after this section. Okay, so first step, I'm going to rewrite it as x to a power. So it's x to the power of 1/2. And now we're going to take the derivative, applying the same principle, bring the power down, subtract 1 from the power, 1/2 minus 1 is -1/2. And let's rewrite without a negative exponent, keeping the 1/2 up front. Now, when you bring it down, it'll be x to the +1/2 power, but x to the +1/2 is the same as square root of x. So I can write it like this, 1 over 2 root x. As a matter of fact, I would say it's a good idea sometime, later on in this chapter to try to remember that the derivative of root x is 1 over 2 root x because it's going to come up a lot. Yes, you can apply those 2 steps if there need be, but I think it's a lot easier if you try to remember that as the derivative of square root of x. Okay, let's try this one, the cube root of x. So we're going to begin the same way. This might be an excellent point for you to pause the video and then come back in a few moments to check your answers. So first I'm going to rewrite it as x to the 1/3 power, right? Because here there's a hidden exponent of 1. That becomes your numerator. The index of the root becomes your denominator of the power, right? So this is just a simplification from algebra. We have not yet done any derivatives. We just simply rewrote it. Okay, now let's take the derivative. Bring the power down, subtract 1 from the power. Okay, 1/3 minus 1, or 1/3 minus 3 over 3, that's negative 2/3. And I can write that as 1 over 3 times x to the 2/3. Now, yes, you could write this as a radical also, but typically I'm not going to ask you to do that unless it's a square root of x, then do it. Just for this one, let's try to, practice our algebra muscles a little bit in our brain. What do we know about x to the 2/3? How do we write as a radical? Remember, the denominator gives you the root, so it's going to be the third root, and the power of the numerator of the power gives you what goes on the inside. So it'll be x to the second power and the cube root of that. So 1 over 3 times the cube root of x squared, or you can just leave it like this. The only way I don't want you to leave it is, if possible at all, don't leave it as a negative exponent, because it's just not simple enough. Sometimes you have to solve an equation, you have to set this equal to something. It's a lot easier if you don't have a negative exponent. Okay, let's try another one. 1 over x to the third. Again, for these two, please try them on your own and then come back, check your answer. So first I rewrote it with a negative exponent, or x to a power, right? Then I can apply the power rule. So bringing the power down. Okay, remember, you're subtracting 1 from the power. It'll be negative 4, right? And rewriting it without any negative exponents, we get negative 3 over x to the 4. And let's try the last one here. Derivative of 5 over the square root of x. First, let's rewrite it as 5 times this. Okay, so when you bring the square root of x to the top, it'll be x to the negative 1/2. It's a constant multiple, so keep the constant as it is, as always. So bring the power down, negative 5 over 2, and subtract 1 from the power. That's like subtracting minus 2 over 2. So negative 1/2 minus 2 over 2, that's minus 3 over 2. And we can rewrite this as negative 5 divided by 2 on the bottom, and also with a positive exponent of x to the power of 3 over 2. Okay, so it's pretty basic. As you can see, it's a huge benefit compared to the longer formula from the last section. But yet you still have to be careful. There are like so many little negatives and radicals or fractions, so you have to be careful with each step. Now there's another rule I want you to be aware of. If you have a sum or difference, derivatives are very easy. You can basically distribute your derivative operation over the first and over the second. Now in a little bit, in the next segment, we're going to see that you cannot do this with products, okay? You cannot distribute a derivative operation over a product, but you can do so over a sum or difference. So derivative of f of x plus or minus g of x equals the derivative of f of x plus or minus the derivative of g of x. Now let's do this next example. So we're going to take the derivative of 7x to the 5 minus 4x squared plus x to the 3 over 3 minus 2 over x squared plus 5 times the square root of x. A long expression. It looks intimidating perhaps, but think of each one as a separate problem from above. Like this would have been one question that we already know how to do. We already know how to do, etc. So if you look at them one by one, it's really not that bad. So let's go. Before I differentiate this, I'd like to rewrite everything with powers of x. I think that's always a good habit. The first two are already in good shape. Okay, the next one, the 3 is in the denominator. I'm going to write it as like 1/3 times x to the 3. The next one, the x squared is in the denominator. I'm going to bring it up as a negative exponent. So it'll become negative 2 times x to the negative 2. And then the last one, 5 root x, I can write that one as 5 times x to the power of 1/2. So now I'm ready to take the derivative term by term. Now, as I'm taking the derivative, the d over dx sign will disappear. It's kind of like saying, like, if I have the square root of 4, once you take the square root of 4 is 2. I don't need to put squared here. That would be wrong, right? So once it does what it's supposed to do, it disappears. Okay, so 7x to the 5, the derivative will be 35x to the 4th. And at this point, you know how to do each one. So this will be a great example for you to try first before you check the answer. Okay, the next one will be minus 8x. The next one, again, bring the power down. 3 over 3 is 1. That disappears, and subtract 1 from the power. It just becomes x squared. The next one, bring the power negative 2. Negative 2 times negative 2 is plus 4. Subtract 1 from the power. X to the negative 3. Once again, bring the power down. Subtract 1 from the power. Becomes x to the negative 1/2. And I'm just going to rewrite everything with no negative exponents. 35x to the 4 minus 8x plus x squared minus 12. Okay, here I want to put in the denominator. Sorry, I don't mean to take another derivative there. So it was plus 4. All I'm doing is rewriting it, bringing it to the denominator as 4 over x to the 3rd. And then do the same thing at the end. 5 over 2 is already there. And bring down the quantity to the bottom as x to the 1/2, also known as the square root of x. So the last term becomes 5 over 2 times the square root of x. So again, this will take some practice, but imagine it's still saving us a lot of time compared to the long formula from the last section using the limit definition. And here are a few more examples before we go to the product rule and the quotient rule. So for instance, this one right here, you may recognize that one from last session. So we want to take the derivative. Now we're using the other notation, the prime notation. So s prime of t represents the derivative of s of t with respect to t. Let's get the derivative of the first term. So the function is negative 16t squared plus 500. So it becomes negative 32t. And what happens to the last term? If you take the derivative of 500, that disappears, right? So this is the derivative at the point t. But I want to know what the derivative is at the point 3. So I'm going to plug in 3 for t. So it becomes negative 32 times 3. And we're getting negative 96. Do you remember this number from the last lesson? Amazing, right? We did so much work. We did a table of values at first. We did the long definition to get this negative 96. Right now, just like 5 seconds and we have the answer. And again, it's very powerful because say I want to know what happens at the point 5. I'll just plug in a 5 in there. So a very simple process, and it's doing a huge amount of work on the background. So that's why we love the shortcut rules. Okay, so I'm going to give you a little bit of time now to do this one, and I will not solve it to save time here, but I'm going to show you the answer momentarily. So please pause the video and come back to check your answer. All right, so there is our answer up there that you can check your answers. And I want to quickly share with you the proof of the power rule. We learned that x to the n, the derivative is n times x to the n minus 1. But why is that? So everything goes back to the basic definition of the derivatives and applying everything back into this basic formula. So if you plug in x to the n and you want to figure out what is f of x plus h, you would take the x out and replace it with x plus h, and you would get this, minus f of x over h. And if you plug in h equals 0 right now, you're going to have 0 over 0, which is indeterminate. But there are certain rules from algebra that we can use to simplify the binomial x plus h to the power of n. Now, I'm not going to get into too much detail there, but you can always look at your binomial theorem notes from pre-calculus. And there is a way to simplify it like this, okay? And then you're still subtracting the minus x to the n. Notice the first terms are going to cancel, okay? And then what is left behind, every one of them has an h in it. This one is h, this one has h squared. So you could factor out h from all the remaining terms, and that's what we do here. We factor out the h, and this is what you have. And at this point, this h cancels with that h, and then you would plug in h equals 0 in the remaining terms. And notice all the terms after the second one, they have an h in it. They're all going to disappear. But when you pull the h out of the first one, that no longer has an h in it. So that's going to stand strong, even where everything else goes towards 0 as h goes to 0. So you're going to be left with n times x to the n minus 1, which was our formula. So yes, that formula is perhaps really long to use, but just know that it's the foundation for all the shortcut rules. And in the next segment, we're going to take a look at 2 more shortcut rules. One is known the product rule, the other one the quotient rule.